All right, let this be your, in essence, gigantic overall probability review. So you can fill in this note sheet as you'd like, or you can just remember all of this, whatever. This is basically a lot of very general information up to very specific information. So first off, when we talk about probability, we're always talking about random behavior. So when behavior is random, and I have a really hard time writing in these small spaces, so individual outcomes are uncertain, but if you look at things over a long span of times, you can sort of figure out maybe what some outcomes might be. And when that happens, we don't know a particular outcome for sure, but we're going to look at a giant a series of events. We call those specifically or individually a random event. And many things in life are considered to be a random event. Probably the most common ones are rolling a die or rolling or flipping a coin. So again, if you roll a die once, six-sided die, I cannot predict for sure what it'll land on. But if I rolled it 60 times, I would expect, I wouldn't know for sure, but I'd expect it to land on one about 1/6 of the time. So about 10 times. And 2 about 10 times, and 3 about 10 times. Not exactly, but probably pretty close. And the more I rolled it, the closer it would come to what I would expect it to be. So that leads us into a discussion of what probability is. And the probability of an outcome is the proportion of times it would occur over a large number of repetitions or in the long run. So these are always based on long run estimates, not on short term kind of events. So the probability of a die landing on 4 is the proportion of times it would land on 4 for a large number of repetitions. We would assume that would be 1 out of 6 in the long run. But again, if I rolled it just once, it either landed on 4 and it's 1 out of 1, or it didn't and it's 0 out of 1. So you can't really look at it in terms of a short series of events. If I look at all the possible outcomes of an event, we call that the sample space. And sometimes recording the sample space is helpful to see what all of those outcomes are and to create our probabilities. So if I were to roll a die and observe what number it lands on, my sample space would be all the possible outcomes, which would be landing on a 1, a 2, a 3, a 4, a 5, or a 6. Those are it. That's it. Six-sided die. There's no other way it could be. If I want to look at a particular event, an event is any outcome or set of outcomes from within a sample space. So you look at your entire sample space, and if you break it down into particular things that could happen, we call those events. So example one, flipping 3 coins. An event may be getting any particular result. It might be just getting a heads followed by a tail followed by another heads. That is an event. But if I flip 3 coins and my event has to do with something about getting 2 tails, well, there's more than one outcome that would have 2 tails. I'm not going to write it up here. I'm going to write it up here. I could have the first 2 could be tails and then a head. First one could be a head followed by 2 tails, or it could be tails, head, tails. All 3 of those events have 2 tails, so that event has 3 outcomes instead of just 1. And we usually denote an event by a capital letter. And for example, if I call getting 2 tails event A, the probability of event A is denoted with a P, and you put the A in parentheses. So this would be talking about the probability of getting A. Very quickly down here, the probability of an event is always between 0 and 1. Cannot be below 0 and cannot be over 1. Probability of 0 indicates the event will simply never occur, cannot happen. And the probability of 1 indicates the event will always occur, meaning it is going to happen every single time. So any probability can be given as an inequality between 0 and 1. If I look at the sample space, the probability of the sample space is always going to be 1 because some outcome in the sample space is guaranteed to occur. All right, turn the page. Here we go. The probability that event A does not occur is 1 minus the probability that A does occur. So a lot of weird language in here, but does not occur. 1 minus the does occur. The A will not occur is called the complement. That might be an E, sorry. And it's usually denoted with a little C up there. Could be a little tick mark, kind of like a derivative. There are other ways. It could put a little bar over it. Could say a little squiggle A. Could be really weird and do this strange bracket A. All of these mean not A. So when flipping 2 coins, the probability of getting 2 heads is 0.25. Probability of not getting 2 heads is the complement of getting 2 heads. So it would be 1 minus 0.25 or 0.75. Some more language that we need to be aware of. If events A and B are mutually exclusive, that's a lot of words there. Mutually exclusive, and another term for that is disjoint, then they have no common outcomes at all, nothing in common. Then the probability that A or B occurs is the probability that A occurs plus the probability that B occurs. So if you see or, you're automatically going to add. So this would be the probability of A plus the probability of B. And that's only true if they're mutually exclusive, if they have no common outcomes, if they have no overlaps. And I want to know what probability of A or B is, I just add them up. So if A is rolling a die and landing on an even number, and B is rolling a die and landing on an odd number, the possible outcomes for A, since they are just even, are 2, 4, and 6. The outcomes for B are 1, 3, and 5. No common outcomes. Evens and odds don't have an overlap. And so if I had to find this, it would be the probability of event A plus probability of event B. And in this case, there are 3 out of 6 that are even, and event B is 3 out of 6, and that actually adds up to 1. So getting an even or odd ends up together as my sample space. Events A and B are considered to be independent, another big word, and independent and mutually exclusive are not the same thing. Independent. So you need to realize 2 different things. Independent is knowing that one occurs does not change the probability that the other occurs. So if I roll a yellow die and a red die, event A is the yellow die landing on even, event B, red die landing on odd. These 2 events are independent because they actually do not impact each other at all. The yellow die has no idea what the red die is doing and vice versa, so they don't change the possibility of each other's outcomes. So if events A and B are independent, then the probability of A and B, that's the word and, equals the probability of A times the probability of B. So when you see an and, you're going to think multiply. So A times probability of B. Again, this is only true if they're independent. You cannot do this if they are not independent. So in our case, the probability that the yellow die lands on an even number and the red die lands on an odd number. So A times B, and it's a half chance that it's even for A, a half chance that it's odd for B. So there's a 1 in 4 chance that it happens that you get yellow that's even and the next one, the red, is odd. If events A and B are independent, then their complements, A complement and B complement, are also independent, and that AC is also, or the complement of A is also going to be independent from B. All right, moving on. Switching colors on you again. All right, the probability that event A occurs if we know for certain that event B will occur is called conditional probability. So another type of probability. This is the fun type of probability. The conditional probability of A given B is denoted by probability of A, vertical segment B. So the word given is what that little segment means, and notice that B is what I gave you, and that's what follows. So literally that order, and that means I already know that B happened. What's the probability that A also happens? So if events A and B are independent, then knowing what that B happened will not change the probability of A. Literally, that's the definition of it. So that the conditional probability then, if they're independent, is equal to the probability of A. And so we have two different ways that we can prove independence, and I'll talk about those at the end. So in this case, flipping a coin twice, what's the probability of getting heads on the second flip if the first flip is a head? Well, event A, getting head on the first flip, well, that's a half. Getting ahead on the second flip is a half, but just because I got a head on the first flip, the coin doesn't remember, so the probability of this is still just going to be a half. That's just the way it's going to be. Didn't change. Knowing that I had a head to begin with doesn't change the probability that I get a head on my second flip. All right, now we're going to get into some exceptional probability language. We're going to talk about the union of events, and the union of two or more events is the event that any or all of those events occur. So addition rule for union, and again, or, this or is the same as union, and union means, or means add, I already told you that, but these are not mutually exclusive. Notice mutually exclusive would be two circles that don't overlap. These overlap, so if they overlap, I have to take away their intersection. The union graphically would be everything in A and everything in B and everything that they have together, but notice that that together part is both blue and red. That's why I have to subtract it, because it got counted twice. All right, the intersection of two or more events is the event that all of those events occur simultaneously. So at the exact same time. So if this is event A and I'm interested in event B, notice that the only part where they actually occur simultaneously is this little part here, that's the overlap. So that is the intersection. And the addition rule for the intersection is basically, I'm just going to take this formula. Here's my intersection. I'm going to move it over here, and I'm going to move the union back. So it's pretty much the same formula. It's you add the two and take away the union. But most of the time, you're just going to see it this way. But you could work it backwards if you had to. All right, a couple examples, and we're going to create something called a Venn diagram here. All right, so we have a situation up here where I have 36 students total. 25 of them listen to rap, 22 listen to alternative, and 16 listen to both. So I've got 25 that like rap, I got 22 that like alternative, and I got 16 that like both. So, and I got a total of 36. So I can do these without a Venn, and then I'll show you a Venn. A student likes to listen to rap. Well, 25 out of 36 listen to rap. The next one is student listens to alternative. Well, 22 out of 36 listen to alternative. The student listens to rap or alternative. Well, okay, so that's the people that listen to rap, right? So that's 25 of them, plus the people who listen to alternative. But I just counted these 16 people are already mixed in with these, so that's where I've got to take away my overlap. That's your minus your overlap all over 36. So if I do that, I get 47 minus 16 equals 31 out of 36. Otherwise, if I don't take that overlap away, notice I have 47 people. That's more than I have, so you know there's a problem. Likes to listen to rap and alternative, that's your overlap. That's just the 16 out of 36. If I want to do a quick Venn diagram here, which are always fun, make a big box. I've got a circle for rap music, and I got a circle for alternative music. And I always start with the overlap. There are 16 kids total that like both, and my red circle has to add up to 25. I've already got 16 in there, so this could only be 9. Rap circle adds up to 25. My alternative has to add up to 22, so this can only be 6. And notice that these add up to 31, which is my number up here, and there are supposed to be 36 kids. That means 5 kids don't like either of those. It's kind of crazy, those kids. Who knows what they're doing? All right, I'm going to jump down here real quick and talk about conditional probability from a Venn diagram. There's a formula for it, and if I want the probability of A given B, that means I only care about B, right? That's it. That's all I care about. That means B is my denominator. That's my new sample space. This restricts my sample space. And the probability that A happens is just this piece of it, because that's the only part of A that's in B, so the numerator is the probability of A intersection B.